get, I should have done this first. No, wrong. Hit the wrong key. Here we go. Okay, now we'll go back. We're recording now already. As soon as I take my finger off, it dies. Okay. I wonder, I don't know how I'm going to do this. All right. Oh, there were some questions, right?
Yes.
Were there questions?
Yes.
All right. So I'm going to go to the white slide. Oh, it might help to turn on the projector. Yeah, I've got it plugged in and everything, but have not yet turned it on. Oh, and turn on. Right now. I'm really in good shape today. Technology is wonderful. It works. And so far, this is working. I'm also going to adjust the lights here. Okay, that's a little darker, isn't it, than this? Yeah. All right. Ah, good. I think good. Why is, oh, that is my screen. Okay. I was going to say, what do I have not? Okay. So what we got for questions?
Basically showed us how to do number 29.
This is on page 131?
128.
128. Okay. Turn back to that page. 128, number 29?
Yes, sir.
Okay. Well, let's see how I'm going to do this. See, my battery I know will not hold out the whole class, so well, what I'll do is write what I can and talk holding the thing down. You say number 29? So this is page 128. Let me get my pen set up. Page 128. Problem set 5.2. Number 29, you said, right?
She showed us how to do number 29. Go to 31.
Okay. Do 29 first, you said.
Yes.
Right? Okay. All right. Find the acceleration. So that means we're looking for acceleration. That's the unknown here, right? Okay. Find the acceleration produced by a force. So I like to call it net force. Here is 6.75 times 10 to the 6 newtons. 6.75 times 10 to the 6th newtons. That is a 6 there. It's sort of ugly. On a rocket of mass, so the mass of the rocket is equal to 5.27 times 10 to the 5th kilograms, mass of the rocket. And what it's asking for is find the acceleration. All right. Now, how would you proceed?
Am I subtracting first?
Okay. No, let's not do any subtraction. Let's find a formula that relates acceleration, forces, and mass. Yes, I.
Oh, F over M?
Okay, yeah. What you said is acceleration is equal to net force over m. Perfect. Okay? I've lost power again. There we go. Okay, let me see if I can hold this with my right hand while I write this way. All right, so the net force is 6.75 times 10 to the 6th. And Newton. What is Newton in basic units? Okay, it's kilogram meter per second squared. Now, the easy way to remember that, or sort of keep your head around it, is that a force is a mass times acceleration. Mass is kilograms, acceleration is meter per second squared. So that's the unit for force. That is what a Newton is. It is what it is, okay? And you're going to take that and divide it by 5.27 times 10 to the 5th kilograms, okay? Now, one of the first thing I'm going to do here is notice that the kilograms are going to cancel out, right? You got one in the numerator, one in the denominator, they're going to cancel out. That leaves you with a unit of meters per second squared, which is a great unit for acceleration, right? So if the units work out well, then there's a really good chance you're doing the problem right. Units are your friends. Pay attention to them. All right, now the next issue is, do you know how to, on your graphing calculator, it doesn't have to be a graph, your calculator, your cell phone, whatever, do you know how to use scientific notation? That's the question. You don't know how to enter it, okay? Let me see what you got. I'm going to let that go without the power on it for a minute. Let me see what you got, because different computers or calculators are a different way. You going to your calculator?
Yes, sir.
Okay. You got, okay. Right, okay. 6.75. 6.75. What is going on here? Okay, now, what you're doing is trying to get an exponential form. So what you look for is this button right here says EE. And it's in blue, so you hit the second first, and then EE, and...
It was under.
Oh, I'm sorry. I did it wrong one. So, okay. Okay. Second, EE. Okay. Now, and it shows the E there, then type in a 6, divided by, okay, 5.27, second EE, 5, and hit equal. What do you get? That should be the number. What do you get? In my mind, it should be something greater than 10. Okay, not a lot greater, but a little bit more than 10. What do you get?
12.
A little louder.
12.8.
12.8. Okay. What's the next digit?
0.
12.80. So 12.8 is certainly good. So the answer is the acceleration is 12.8 meters per second squared. Whoops, it's not working. There it is. Okay. You see how that works? Now, if you got a graphing device that doesn't have the EE key on it, pull up what you got and let me see, and I'll see if I can find. Sometimes the key is EXP. You use those keys, you can do scientific notation much easier.
I just bring mine on Tuesday.
Okay.
This one just got the regular calculator.
That might be a good idea. Sometimes the phones, it depends on what they got in them, but it's they'll do the stuff, but you have to figure out how to get them to do it. So is that the answer in the back? You do know in the back of the book are answers for odd numbers anyway. I have a piece of paper holding my place back there, okay? After the one that's holding the place for the tables, and this is 5 point.
Yes, sir.
It is the answer? Okay, good deal. All right, did that answer what you needed?
Yes, sir.
You need another one?
31.
31? Okay. I'm going to erase what we got here. Everybody got this now?
Yes, sir.
Okay. So let's erase this and go to 31. Same page, same everything. So number 31. Okay. Get my power back on. Okay. 31. A discus thrower exerts a force of 140 newtons. So we're given a force, F, and we assume this is a net force, and I think I just lost power, okay, is equal to 140. And what does that bar there mean? Newton. That bar over the 0. You remember? That means that's a significant digit. The 0 is significant. If the bar wasn't there, you'd have to assume that's just 2 significant digits, 1, 4. This is 140, okay? Now the A part, if the discus has an acceleration of 19.0 meters per second squared, my word, that's a big acceleration. A is 19.0 meters per second squared, okay? Okay. What is the mass of the discus? So we're looking for the mass. What would it be? Next thing you ask yourself is what formula relates force, acceleration, and mass? Same basic form. Yeah, what is it?
It's F over M, so force divided by mass.
Okay, that's if you're looking for acceleration.
Oh, yeah.
Just flip those two, and it's force divided by acceleration. Perfect. Okay, so let's put the force down. Well, it's 140 with a bar over the 0. Now let's write the fundamental units of newtons. What is that? Kilogram, meter per second squared. Now the symbol M as a parameter is mass, as a unit is meter, okay? And units have numbers in front of them, so that's what gives that away. The acceleration, 19.0, and that 0 is significant too. You don't need a bar over it because it follows the decimal place, and that's meters per second squared, okay? Again, units are your friends. Take a look at this. The meters per second square here cancels out the meters per second square there. And that leaves you kilograms, which is a great unit for mass. So the mass is, and this one you don't need a scientific notation. It's just there. For 140 divided by 19.
7.37.
7 point what? 27? 37. And what's the next digit?
The next digit.
Say again?
What do you mean?
The next digit after 37. What is it?
It was 36.
Oh, 36, and you've already rounded.
Yeah.
Okay. Can't get my eraser to erase. Let me see if I can. Ah, there we go. So you've already rounded it, and that's units of kilogram. Is that what they got in the back? Put your piece of paper back there to hold the place. I would, but I got to hold the cord in place. This is weird.
Yes, sir.
7.37 kilograms. Excellent. See how that works?
Yes.
Now again, do y'all like circles or triangles better? Just make up one. Triangle, okay? Again, let me show you that triangle. It has a dividing line and then a multiplication line. The thing that's equal to the product, that's the force, is equal to mass times acceleration, Newton's second law, right? The formula that best exemplifies it, okay? In that first problem, we were looking for acceleration, so you cover the A, and you have force divided by mass. That's what we used. In this problem, we're looking for mass, so cover the M, and you have M is equal to force divided by acceleration. So that'll do it. As long as you get those three in the right place, you do it. If you're looking for force, cover force, it's mass times acceleration. So that's how you set it up. You just sort of have to know how to set that up, set it up properly, and then you can get all your equations from that on this one. Any others? Say that again, 27? Is that why I'm hearing 27? Okay.
You done with 31 or you finished like that?
Say that one more time.
You still doing on 31?
No, 30. Oh, wait. There's more, isn't there? Okay, I'm sorry. Okay, that's just the A part. Now it says if the mass of the discus is doubled and the applied force remains the same, what is the new acceleration? So this was the A part. Okay. The B part is you're going to double the mass. Oh, I'm about to lose my book. Okay. Now, I'm going to do it just by what y'all gave me. It may be a little different. The mass is now 14 point, it would be 7.4, so I'm just going to round that to 7, 14.7 kilograms. Force remains the same. Net force is equal to 140 newtons. Okay? So it says what would be the new acceleration. What would that be?
For acceleration?
Yep. Force divided by mass. So net force divided by mass is equal to 140. And what the basic units for newtons? Kilogram, meter per second squared, divided by 14.7 kilograms. I can't write, but that's supposed to be a kilogram. Notice here the kilograms cancel out, leaving you meters per second, which is a great unit, meters per second squared, for acceleration. Okay? And punch it in the calculator, see what you get. I'm just going to make a guess right now while you're punching. About 19.5. I'm sorry, 9.5. Tell me if that's what you get. 140 divided by 14.7. 9.5? 9.5 what? Need another digit there. 9.50 or what? 2? 9.52. Kilogram, meters per second squared, not kilogram. Meters per second squared. All right. Is that what they got in the back? Is that what you had? You said? I thought that's what you said.
It is 9.50.
That's what I would have guessed is 9.50. And here's why, folks. Okay? That 14.7 was a round off, sort of. But all you have to do, if you double the mass, which is what we did, you're going to half the acceleration. So the acceleration would be 19.0 divided by 2 would be 9.5. That's why I was able to guess that. So that would have been the easier way. So 9.50 meters per second squared. 9.52, that wouldn't be bad because it's pretty close, but you know, that's right. So that's the B part. The C part, if the force is doubled and the mass is unchanged, so we're going back to that. So now the force for C, can I go and erase my
Yes, sir.
my triangle? Is that all right to do? Yes. Okay, because I need the room to write. Okay, okay. All right. Static friction means, you almost see the word in there, stationary. That's the friction when nothing's moving. That's the friction you have to push to get it to move. Okay? Static friction is usually greater than the other friction is kinetic friction. T-I-C, I think is how you spell it. I had to stop. That's the friction of motion. Once it's moving, it moves pretty easily. And I don't know if you've ever done this or not. Have you ever been pushing on something that's really hard to push, and you're pushing and just really pushing on it, so then when it finally moves, you almost fall down because once it's moving, the friction is less. Okay? They do it in cartoons a lot. I don't know if it's in real life, but I do know I've had that experience myself as well. So the static friction is usually greater than or sometimes equal to, that's supposed to be a greater than symbol. That's pretty ugly. Let me get my, where is my, there it is. Okay. Greater than or equal to kinetic friction. The force needed to get something moving is usually greater than the force to keep it moving. Okay? And that's at the top of page 132. Now, here are three kind of comments about friction. So I'm going to erase the one I've got here. Is that okay?
Yes, sir.
Okay. I'm going to write these three experiments for frictional forces indicate the following general characteristics. The first of these. Okay, now don't get too hung up on this. We're not going to be a big deal, but it's just something you kind of need to know. Friction is a force that always acts parallel to the surface in contact and opposite to the direction of motion. Friction is parallel to the surface. I'm really lazy. I use the symbol two parallel lines for some parallel. And opposes the motion. Okay? When I pulled on the desk, the friction was that way, opposing my motion. Okay, but I did get it to move. But then when I went to push the desk back, now the friction's this way, opposing the motion. It always is opposite to the attempted or actual motion. So there's the first characteristic of friction. The second one, and that's the one we just had here, is that static friction, I wish I had still left it up there, friction, is usually, I actually put, they say greater than, I say greater than or equal to kinetic friction, the friction of motion. Okay, there's the second one. Okay, now the third one of these is this one. Okay, and now I'm going to go to the next slide. In fact, I meant to be on the next slide when I put the first two, and then I realized I wasn't. Here's this one. Friction increases as the force between the surfaces increase. So here's the third statement. Friction increases as the force between the surfaces increases. Now, I wanted to be there because that's what this is showing, but I want to go back a slide too. Okay? Let's just imagine this block right here, that's not the same as that, but the block right here has a certain weight on it. Okay? Then that's going to tend to push these things down in the grooves a little bit more. Okay? Well, what if I put more weight on it? Then it pushes them down even harder. So that then, even though the motion is this way, not down, it makes it harder to move because now you have more to lift and more to overcome to get that to move. So if you add more force, and that's what they're saying here, the friction increases as the force between the surfaces increase. So here in the first one, you have a crate here, and you're trying to pull it this way, so your effort is this way, trying to pull it this way. The friction force is going to be that way. Take the same crate, another one just like it, and put another one on top. Okay, now you've got twice as much weight down on the surface, so you're going to have basically twice the frictional force, so you're going to have twice the effort to move that. Okay, that kind of makes sense, right? Okay, so that's the third characteristic of friction. All right, now, we're missing a formula, aren't we? We can't do too much without having a formula, so let's go on and put the formula in here. The force due to friction, F sub F, F sub W is force due to weight, or weight. F sub N is the net force, the total force, okay? The force due to friction is equal to, this is called the coefficient of friction. Now, you can have a subscript of it. That's the Greek symbol mu, which is like our little m. It doesn't look at all like the little m, but it's the same letter in the Greek alphabet that corresponds to our m. That would be a lowercase mu. And actually, there's two mu's, okay? You could have mu sub s if that was static friction, or you could have mu sub k if that was kinetic friction. Two different mu's, but the formula is still the same. So we're going to do the formula at, not what I wanted to do. We're going to do them as if, doesn't matter which one we're using, S or K. So let me go back and get my pen back, okay? So the force due to friction is mu times F sub, now this is a capital N, not a little n, which I was using for net force. And this is why this book doesn't use net force, because they use F sub N to mean the normal force. Okay? So, now this sounds really stupid, but it's really true. It's not the weight of the box on the surface, it's the force of the surface on the box. That's called the normal force. Okay? So weight is always pulling downward, the normal force is pulling upward. If you remember my illustration of walking across the plane, and you said it would pop on me, yeah, thank you so much, okay, for that confidence in my weight, okay. That true, the board is pushing up with a normal force perpendicular, equal to, possibly, or less than my weight. If it's less than, then I'm going to break the board. So that's what it is. This is your normal force. That's the force pushing up by the surface. So it's a little, seems like a picky thing, and in this case it wouldn't matter because the weight down due to gravity is exactly the same as the normal force up. Here's the place where it's different. I don't think they're going to show you this, so I'll is it? Man, just when we were beginning to have fun. Oh, we were always having fun, weren't we? Always, okay. All right. We will stop there and pick up next time with that coefficient of friction. Okay? Let's see. Oh, we didn't do any new exercises here, did we? Examples. So no new homework exercises. Keep working on the ones you were. And didn't get too much covered tonight. Sorry, my computer messing up. Now it's just doing great. I don't have to hold it or anything. It's doing fine. But sorry that took more than 30 minutes of the class. And then we did answer a lot of questions, which I'm glad to do always. So we'll pick up and go from there.
You want me to get it again, Thursday, the card?
What's that again?
Get the card again?
If you want to do that, if you're here first, yeah, you can certainly do that. And that way I won't have to stop down there.
Well, don't stop out here.
Okay.
Have a good night.
All right, you too. Thank you.